Hi, it's Lee from the Japanese Water Gardens. Welcome to my step-by-step guide to installing an Oasa gravity-fed drum filter. An automatic filter that flushes itself clean and requires only a moderate amount of maintenance. If installed correctly, a drum is arguably the most efficient and easy to maintain koi pond filter. In this series of videos, I will explain how to connect your drum to an aerated bottom drain, fit a simple water auto top-up with built-in overflow, and pipe in your pump, UV and skimmer. Even if you're not opting for a drum system, there is a huge amount of extra information you will want to know before you construct your pond. So get sat down with a coffee and let me show you how I would go about installing one of these amazing filters. Hi there, welcome to part 4 of my step-by-step guide to installing a gravity-fed drum filter. In the previous videos, we built up this pond with a bottom drain and skimmer, then installed the Oasa drum filter, talked about pumps, and then fitted an auto top-up system. Please make sure that you watch those videos first, otherwise this one might not make much sense. In this video, we're going to be taking a closer look at water returns, fitting a UV, and connecting up an air pump. It is not uncommon for people to build a filter enclosure with a fabulous roof and door, only to discover that the filter system is too big to go through the door. This is a mistake that I have actually made myself in the past. Make sure that you allow plenty of space for all of the accessories, pipework, and everything else that you're likely to need now and perhaps in the future. If you don't mind the equipment being on show, the enclosure is not essential. The pumps, the UVs and the drum are all made to weatherproof standards. But to do a professional install, it is highly desirable. A simple design with a large swing gate often works best. A very common mistake that I see people making is running a high output pump on poorly designed, inadequate, restrictive pipework. The more complicated our pipework, the longer the pipe runs, the more fittings we install, the more the flow will be reduced. To build a successful pond, you don't need a degree in fluid dynamics. You don't even need to refer to a complicated friction loss chart. But a basic understanding of how pipework affects pumping rate is essential. When you buy a pump, it will usually be marked up with a figure indicating the maximum flow in litres per hour. This figure is the amount of water your pump can move out the discharge port when there is no pipework connected. Obviously, this is of no practical use, so we need to attach a pipe to our pump. Now the pump is performing a useful task, but the output rate will have taken a hit. Our 10,000 litre per hour pump will not be pumping 10,000 litres per hour. One reason for this is the pump is now lifting the water. You might have heard the term pumping head. It refers to the vertical distance the water is raised in the pipe. The greater the lift, the slower the water will flow. But there is a lot more going on here that is also contributing to this reduction in flow. The pipework itself is restricting the water flow. Flexible pipework is often best avoided. Not only does the irregular inner surfaces create friction, but it connects to the pump by means of a hose tail. The hose tail is in fact a blockage in the pipe, a bottleneck. On a typical pond, you will also have a UV and perhaps a heater. If you're using flexible pipe, that means lots and lots of hose tails, lots of bottlenecks. Aside from the restrictive nature of flexi pipe, it is also prone to leaks, and it can quite frankly be a sod to connect up all those hose tails. Lots of reasons why you would want to find a better alternative. Solvent weld pipe is far superior to flexi. It has a smooth inner surface that allows the water to slip through with less effort. When it is connected to the pump or a UV, the fittings slip over the pipe, so there is no bottleneck. The reduction of friction can result in a much improved flow through the pump. Now the pipework will still be causing some friction. The pumping head will still be a factor, but the flow will be closer to the pump's maximum flow. You will often hear people explaining how much a restriction a 90-degree bend will put on the flow. Upgrading to swept bends or using 45-degree bends can reduce some of this restriction. But there is a massive difference in price between standard bends and swept bends, and the benefits that you can actually get from them may not be worth it. What is definitely important is using a pipe size that is appropriate for the flow. Reducing the pipe diameter can dramatically have a negative effect on flow. If the pump has a 2-inch outlet, then this is a good indication of the size of pipe that's going to be needed. Running a big pump on a narrow pipe is a very common mistake. There are no hard fast rules about pipe sizes. The wider the diameter, the less friction. You will never ever restrict flow by upsizing to a larger diameter pipe. But for practical reasons, you're not going to want to run a huge pipe. As a general rule, I would recommend that you use a 1.5-inch 40mm pipe for flows up to 2,000 gallons and a 2-inch pipe for flows that are greater than this amount. This is not to say that you cannot get more water down a 1.5-inch pipe, because you can, but this is the point where you will start to see some major negative effects. Sometimes it will make sense to split the outlet from a pump into 2 or more pipes. There is no problem doing this. 2 1.5-inch pipes is roughly the same as 1 2-inch pipe. Provided we avoid any bottlenecking, the results are going to be good. This can also help to address the problem of how do you connect up an appliance, such as a UV, that uses a narrow connection without any bottlenecking. The flow rate through a UV is completely irrelevant. It will not matter that some of the water is not passing through it. One more point to make is that the pipe connected to the pump inlet is of equal importance. If the water flow into the pump is restricted, then you will see negative effects on the output. Now we have that little lot out of the way, let's get on and connect up the rest of our pipework. All koi ponds will need an ultraviolet light to prevent green murky water. A simple rule of thumb is to allow at least 10 watts per 1,000 gallons. In practice, most people will install a UV that is much more powerful than this, because they are not expensive, and the pipework on a low output model is often narrow, and this can restrict water flow. I am extremely skeptical about the effectiveness of the so-called UV sterilizers. The purpose of a UV is solely to control green water algae. There is no doubt of its ability to perform this task. You can spend a small fortune on UVs, but I am dumbfounded as to why anyone would. My experience of UVs is that there is little to be gained by spending a lot of money on them. They are all capable enough. All have delicate glass sleeves that often get broken. All can be fiddly when it comes to bulb changes, and so on. Two low-cost models are the 55-watt Konikoi Yumatsu. It has a simple design that has remained unchanged for years, and the Evolution Aqua 55-watt model that looks a lot more modern and is now in its third or so generation. As stated, there is nothing to pick between them in my opinion. Others will beg to differ, I am sure. Both of these models will come with wall mounting brackets. Both of them will use standard T8 lamps. What is important, just as it is with the pump, is to invest in a pair of union couplings, or some means of detaching them from the pipework. When it's lamp change time, having the ability to lift the unit out can be incredibly useful. At some point after the UV, you will need at least one valve. When the valve is shut, you can remove the UV without draining the pond. To help support the pipe, you can buy wall clips. They will help to take the weight of the pipe off the appliances. A few strategically placed clips should firm everything up nicely. The pond return should be opposite the skimmer, approximately 9 inches below the water level. The idea is the return pushes the water back over to the skimmer, feeding the skimmer with surface debris. The return should be built into the pond wall during construction or cut out with a core drill and slotted in. You can use a simple tank connector, or as an alternative, a swimming pool eyeball fitting. It has the added ability to angle the water flow so you can make small adjustments. On this design, we are just using one in-wall return. Systems with a higher turnover will need more than one return. The position of the returns should not interfere with the function of the skimmer. Do not fit a return that is likely to push water away from the skimmer. Inside the drum, we have a chamber ready to be filled with biomedia. When operating, the media will be agitated and it will boil up, moving around, ensuring a good water circulation. An air compressor is required to provide the movement of water. If you invest in a powerful pump, it will have enough grunt to operate the aerated bottom drain as well. If one pump is going to do both, then a T-section will need installing on the hose, and a pair of inline valves will allow us to control the flow. The hose can be pushed over the connector on the side of the filter, and a friction fit is all that is normally required. The hose running to the bottom drain should be connected securely to the air feed pipe. Again, a friction fit can be used, but additional protection should be added to ensure that it can never detach. If the connection is lower than the water level and it was to separate, a large quantity of water would be lost from the pond. Ideally, the air compressor should be mounted on a shelf that is slightly higher than the water level in the pond. This will prevent any possibility of water siphoning backwards and damaging the compressor. If the pump has to be installed lower than the pond water, then a flow check valve is required. However, I strongly recommend installing the air pump up on a shelf. Even the best quality flow valves have been known to fail, and if nothing else, they are a restriction on the compressor. There is no shortage of good quality air compressors available. If you need one to just operate the filter, then a 50 litre per minute model is going to be absolutely fine. If you're looking for one to do both the filter and the bottom drain, then I would suggest about 100 litres per minute would make a better choice. Contact a qualified electrician and have them install a power supply for the pond. The load will be at the very least 13 amp, but if you're going to fit a heater, then the load could be much higher. On our system, we have to provide power for the drum filter, the circulation pump, the UV and the air compressor. I believe the best solution is to install a large outdoor power box with a hinge door and plenty of room for sockets. With a setup like this, you know your pump is off because you unplug it. In the future, you may decide you want to add extra appliances, so it is best to future-proof the supply and make sure that it will be able to deal with anything that you're likely to require. I am not a fan of the multi-switch panels. They might look cool with all the buttons, lights, bells and whistles, but when something needs rewiring in the middle of winter and it's pouring with rain, your hands are cold and it's getting dark, they're just too fiddly for me. In the next video, we will get this pond filled up with water and take a closer look at how best to deal with wastewater. Look out for the next video in 1 week's time. Thank you for taking the time to watch this video. If you like what you see, please subscribe to the channel. Post some comments below. It's bye for now from Lee at the Japanese Water Gardens.